Right, let's have a look at redox reactions and using standard electrode potentials to work out what's likely to happen. So we've seen this table already. We've got the idea of the anti-clockwise rule, which is really useful. Check to make sure the electrons are on the left-hand side. Check to make sure the negative numbers are at the top. Okay, so you're going to have to develop your own system for this, but generally all roads lead to Rome, and all of the systems are essentially the same thing. So the first one, using the anti-clockwise rule, then let's look at an example here. If I've got two systems, Fe3 plus with Fe2 plus and manganate 7 with Mn2 plus, then what's more likely to happen? Well, using the anti-clockwise rule, it's more likely that Fe2 plus ions, iron 2 ions, are oxidized to iron 3 ions, and manganate 7 is reduced to Mn2 plus. Okay, now we know that reaction happens, but you can see here that it's likely to go in that direction. That would be the direction of spontaneous change. Okay, remember there that that's in the presence of plenty of hydrogen ions. It's important that the manganate 7 is acidified. Otherwise, other reactions can take place. So, anti-clockwise rule is one possibility. Another possibility is remembering that the equilibrium with the more negative value for standard electrode potential reveals the reducing agent. So if we look at this, where's the reducing agent? Well, it's magnesium metal, isn't it? So it's more negative value for SEP, and magnesium metal is going to be the reducing agent. So in this reaction, perhaps with silver, magnesium will reduce silver ions to silver metal, and in the process it's oxidized to Mn2 plus. Conversely, the more positive of the two electrode potentials reveals the species that's more likely to accept electrons. Okay, look at the species down here. We're talking about chlorine. It's more likely to accept electrons. So more positive gives us the species that is more likely to accept electrons. Okay, so more negative gives us a species that is more likely to release electrons. That's a phrase that they like to hear in exam questions. The magnesium would release electrons, and the silver ions will accept electrons. Another possibility is to remember classic examples. So if you know, for example, you can intuit that potassium and fluorine, well, you know potassium is going to give its electrons up and fluorine is going to gladly accept them. So you know which way they go. So it's got a negative electrode potential. It's going to give its electrons up because it's a good reducing agent, and fluorine is going to accept those electrons because it is a good oxidizing agent. Zinc and copper we've seen before. So if you've got zinc and copper, you look at those equations. Where's copper and zinc? There's potassium and the oxidizing agents. Copper and zinc, well, copper is here and zinc is here. And you know that zinc becomes Zn2 plus and copper 2 plus becomes copper. Thiosulfate's not on here, I don't think, but you know that thiosulfate's a good aqueous reducing agent, and manganate 7 is a good oxidizing agent. That's down here. It's good at accepting electrons. Okay, just other different systems that are little reminders of how these things work and how you can apply them when you're doing questions. It's important that you develop your own system, but they're all more or less the same thing. Right, try the pages 1991, any questions you come across, and read the text.